The water molecule, one negatively charged oxygen atom, two positively charged hydrogen atoms, in a plane with an angle of 104.5, and each hydrogen atom is located a little less than 1 angstrom, or 10 to the minus 10 meters away from the oxygen atom. Water covers about 70% of the Earth. At 0 degrees Celsius and ambient pressure, the water molecules arrange themselves to make hexagonal ice, known as ice 1H, and found in most of your freezers. By lowering the temperature or raising the pressure, the water molecules can arrange themselves in up to 15 different crystalline forms. In places of low temperature and modest pressure, where water molecules are present along with gas molecules, tonight we will consider mostly methane and carbon dioxide, gas hydrates form. This crystalline structure consists of an ice-like host lattice forming large polyhedral cages where the guest gas molecules are occluded. Gas hydrates are also called clathrate hydrates, and in chemistry it is defined as a molecule of one compound, the guest molecule, filling a cavity with the crystal lattice of another compound, here the ice-like host lattice. To reiterate, we need H2O, low temperatures, modest to high pressures, and any one of a variety of guest molecules. This next slide puts you in the frame of the reference of the pressures needed. Methane hydrate stability starts at about 10 megapascals compared to an alumina scuba tank with a typical pressure of 25 megapascals. Carbon dioxide decomposes at about 800 megapascals compared to the high pressure processing of lobster to remove their meat at about 600 megapascals. Commonly, 3 different hydrate structures can be formed depending on the guest molecule. The hydrate structure is made up of different polyhedral cages. Both methane and carbon dioxide hydrate form structure type 1, made of 2 cages consisting of 12 pentagonal sides and 6 cages made up of 12 pentagonal sides and 2 hexagonal sides. A variety of guest molecules can be occluded, including methane, carbon dioxide, ethane, propane, hydrogen, disulfide. Interestingly, both methane and ethane hydrate alone form structure type 1, but when combined, they form structure type 2, illustrating the complexity of the host-guest interactions. In nature, the necessary conditions of H2O, low temperatures, and high pressures, along with gas molecules, can be found on the seafloor, buried in the sediments and the permafrost. This map from the U.S. Geological Survey shows the locations where gas hydrate samples have been recovered, as well as sites where gas hydrate samples are referred to occur. Recovered gas hydrate samples come in a variety of forms found in different geological settings, including massive mounds on the seafloor, thin veins and muds, mixed in fine-grained marine sands or lenses. Here are some of the samples recovered from marine locations in the Gulf of Mexico. Here we have hydrate samples recovered from the Canadian permafrost. These recovered samples are mixed with coarse and fine-grained sand. One unanswered question within the hydrates community impacting the mechanical properties is if the hydrates fill the pore spaces or if they cement the grains together. The conditions for hydrate formation are often found in gas pipelines, resulting in pipeline plugs that can reduce flow or cause pipeline damage when a large amount of pressure builds behind the plug and the plug blows. The gas and oil industry find these pipeline plugs highly undesirable, and flow assurance engineers work to prevent these plugs from occurring in the first place. The conditions for gas hydrates can also occur on other planets and moons in the solar system. Many scholarly articles discuss the role of carbon dioxide hydrate on Mars, and methane hydrate is thought to have played a significant role in the formation of Saturn's moons. Shown here is one of the moons of Saturn where gas hydrate activity is possible. Remember the Deepwater Horizon oil spill? One idea was to cover the largest leak with a 280,000-pound containment dome and to pipe the oil into a storage vessel. It failed due to methane hydrates forming and plugging the top opening of the dome. The containment dome also became buoyant since the density of methane hydrate is less than seawater and floats. A variety of scientists, engineers, and researchers study gas hydrates. Here's a snapshot of the attendance of the International Conference on Gas Hydrates that occurs every 3 years. The first meeting in New York in 1993, the attendance of the meeting has increased from a little over 100 attendees to about 600. The next meeting will be in Beijing later this year. Other topics of research include methane hydrates' roles in global climate change, and especially as a source of methane. Gas in place is a measure of the total hydrocarbon volume present, and estimates are that gas hydrates, there's somewhere between 10 to the 16 and 10 to the 18 cubic meters. The ocean is roughly 10 to the 18 cubic meters. The Department of Energy and the gas and oil industry are interested in harvesting the methane. There's also been consideration of using gas hydrate structure to sequester CO2. In 2012, DOE and ConocoPhillips performed a test injecting a mixture of carbon dioxide and nitrogen into hydrate saturated sand and demonstrated that this mixture could promote the production of natural gas. I'm going to switch gears now and talk about how, along with my students and colleagues, I've studied methane hydrates in this laboratory. The first, using the seafloor process simulator, a 72-liter pressure vessel that we pressurized with methane and conducted experiments in an explosion-proof cold room and monitored optical fibers for thermal observation signaling hydrate formation or dissociation. A powerful tool for understanding hydrate structure is neutron powder diffraction. Shown here are students at a reactor source and at the spallation neutron source. The inset shows data collected on a hydrogenous sample made with D2O instead of H2O, illustrating how sensitive neutrons are to isotopic substitutions. We synthesize samples and collect neutron powder diffraction data with mixed methane and carbon dioxide gas molecules. This shows nuclear density maps and how they are different for the different molecules in the cages. Blue indicates negative scattering and is related to hydrogen atoms and the methane molecule. The results we obtain from neutron powder diffraction experiments include the volume of the unit cell and the chemical composition, and we can use these results to calculate physical properties like density. Our results indicate that the gas molecule have vacancies, suggesting the actual physical properties are much different than those of the end members. Thank you.